or calcium? Argon. So it's called the argon core, and what's left over? 4s2. How many valence electrons has calcium got? 2. That's pretty much all it's written. So when some of these ladies talk about, well, you're not going to give us Einsteinium, are you? That'd take forever. Yeah, it would, but with this shortcut, it's not that bad. All right. Are we good with that? One more situation, and then I want to show you John's periodic table back there. In the D block, so if you were doing the electron configuration for scandium, go to the noble gas that comes before it, and what is that? Argon. That's a 4s2. Tell me where we're at now. At calcium. Now you think you're at the fourth row, right? But you're really at the 3D1 level. This is scandium. Anytime you do with the D blocks, you use what's called an N-1 rule. And that is wherever you think you are, you subtract 1. So that means everything here is a 3D, right? What's everything here? 4D, 5D, and so forth. And that's it. Everything else is treated the same. Now, what if you had germanium? What's the electron configuration for germanium? Well, the noble gas before it is argon, 4s2. Then what comes next? 3D what? 10. Now, if it's a D10 system, where is it at? Zinc. Now, what comes next? 4p2. Take note, I ain't got nothing drew around the p. When you get back to p, everything's normal again. You know, this is the fourth row, this is the fifth row, and the like. Now, what do you think about, and I've never asked this, what do you think about the electron configurations here? Well, if this is the N-1 rule, what's this one? N-2. These are called the 4Fs, and these are the 5Fs. Okay? But I've never asked those. So I told you. I'm not going to ask you Einsteinium. I won't. All right? But that's how it goes. All right. Are we good? All right. Let me have your periodic table, John. You pass that up here to Bonnie. All right. So this is a little nifty-difty periodic table here that I want to show you up on the board. You can just focus in on the board there. It'll be fine. And this right here is the reason why, and I'm picking on John, this is the reason why that I provide the periodic table on the test. You don't provide the periodic table on the test. All right. What's that now? That's wrong? I bought one of these as well. Mine's all laminated in that. So anyway, let's zoom down on, what's the first thing I got wrote up there on the board? Is it sulfur? Yes. Let's zoom down here on John's sulfur. All right, had a little out of focus there. And what's this doing? Well, it's telling me that there's a neon core with a 3s2, 3p4. Do you see that? What's another one? Nitrogen, helium core, 2s2, 2p3. All right. Calcium down there, I'll just have to run real quick like. Let's look at calcium. Argon 4s2, you see it? All right, let's look at that D block there. Look at what did I have you do? Scandium? Okay. Now, there are two ways to do an electron configuration. One way is to do them numerical. The other way is to do them energetically. Energetically, the 4s is lower in energy than the 3d. So the way I taught you to write it was to put what one first? The 4s first. You see, 4s2 comes first. Then does the 3d. You see, I don't care about your numbers. If low energy is down here on the ground and high energy is up here, okay, this is a 4s energy level, and this is a 3d And yeah, I'm telling you that right. The 3D has more energy than a 4s on a potential energy surface. That's why that your book and me and everybody else teaches you not to do it numerically. All right? Is this wrong? No, it's just a different method. Your book will not do it John's way here. Okay? Now, let's look at your textbook. All right, in the back of your chapters. And I want you to tell me what the electron configuration of copper is. The electron configuration of copper. So go ahead and write that down somewhere as I peruse the book and find me a table. Have I stolen your periodic table, John? Can I keep it for just a minute?
Sure.
All right. So we're looking at copper there. All right. Now, here's what a normal human being would think up to this point. That the electron configuration of copper, well, what's the noble gas right before copper? Argon. All right, so this right here is what a normal person would think. An argon core, a 4, yeah, thank you, a 4s2, a 3d what? 9. You with me on normal? Chemistry, and I cannot stress this enough, chemistry is an empirical science. It's experimental. If you want to know the answer to any chemistry problem, there's only one way to find out, that is get in the lab and do it. Okay? Now, in freshman classes and in every chemistry class, we give you patterns of things that happens most of the time. Now, copper's an example where that don't happen most of the time. What is the real electron configuration for copper? It's an argon core, 4s1, 3d10. Now look at that right there. Do you see that? That is the real measured in the basement with lasers hitting atoms electron configurations. Now why is that? Why is that a 4s1? Should it not be a 4s2? You're shaking your head, yes it should be, and you're right? Because that goes against the rule. That goes against the rule. That one goes against the rule. This is called a coinage metal triad here. Copper, silver, gold. All right. So if you are electrons, what do you like? And you like them in this order. The first thing you want is to have everything full. If you are an electron orbital, you want to be full, just like xenon, argon, krypton, any of the noble gases. Now, if you can't be full, there is a second best option out there for you. And that second best option energetically is exactly half full. And if you can't be half full, well then you pretty much just take whatever is dealt to you energetically. So let's look at this one here. We've got two orbitals, we got two sets of orbitals here. We got an S and we got a D. S is completely full, right? So let's give that a good old check mark. Is there anything up here half full? No. And then that means we're just a whatever.